Hi guys, welcome to the next lecture on the Vhdl lecture series, where today we'll be discussing how to make bigger designs using smaller designs. So as a part of today's lecture, we will first understand what do we mean by a component and how we instantiate or use that component. Then we will see a basic example of component instantiation, and then we will see a full adder example, that how do we make full adder using half adders. So let's begin. So why should we use components? What is the purpose of using this style of programming in VHDL? So first, if I make a design, let's just call it X, which has inputs A, B, outputs C and D. I write this in a VHDL design. And suppose if I would like to use this design X multiple times in another design Y, which comprises of using this design X multiple times. So if there is repetition of designs, if you would like to build a hierarchy, so if you have design Y which comprises of many designs X, so this would be a hierarchy. So to make your design clearer, we will use the concept of components. Just a quick point is that this style of design is called the structural style of modeling, which we saw as a part of the introduction in the introduction to the architecture. So what is component instantiation? Before that, we will understand a few terms. A component is basically a pre-compiled or a pre-designed entity and architecture pair. So you have a working design which has an entity and an architecture, and we will use that as a component. Now instantiation means that using this component in a larger design, not necessarily larger, but as long as you plan to use this component, then the process by which you would do it is called instantiation. And the method of instantiating a component and using it, we call it port mapping, is that we map the ports of my component to signals or ports in my larger design. So let's understand this using an example. We will understand the basic syntax is, if I have a component whose ports are, let's say, A and B, and I want them to connect to signals M and N in my design. So let's say these are my component ports and these are my design signals. Then I would write the component port here and the design signals here. Now every time I decide to call on a component, so for example in our previous example we had the component X, so every time I call on X, I would write X here, but I also have to specify an instance name. So let me call this X underscore 1. Then the next time I would do this same method again, I would say X underscore 2, the component name would be X, then I would write port map, and then I would write the procedure. So let's look at a clearer example. Suppose if I have a NAND gate whose inputs are A, B, and the output is C. And suppose that I want to design a circuit that looks like this. How would I do it? I would first call upon or write the entity of the larger design. So this is the larger design with 4 inputs, input 1, 2, input 3, 4, and output Z. So this defines the larger design, and I would call in the component that was the NAND gate after I write the architecture. I would call in the component with the keyword component, the name of the component, which was ND2, which I decided to give it, write the ports of the component, and then write the keyword end component. So this is what I call as declaring the component. Okay, I hope you are following me. So just a quick recap is that first I will declare the entity of the larger design like I do in any regular VHDL code, and then I will declare the component, and the ports of the component must be same as those defined in the component VHDL code. So you would have written a VHDL code for this AND gate, a NAND gate, and the NAND gate ports, that is A, B, and C, and the ports declared here must be the same. I hope that is clear. So now let's continue on understanding how to use this AND gate. NAND gate. How to use this NAND gate as a part of your design to actually give us this circuit. So first I need to define my signals that will form my internal connections, and this is how I would do. So first I would have my instance name, which is U1. Then I would have my component name, which is ND2. So this is the first time that I'm calling on ND2, where my port A is mapped to my input in1. So my port A is mapped to in1. My port B, the second port, is mapped to input 2. My output C is mapped to my signal temp1. Similarly, I will be calling on ND2 again as an instance U2. See, these instance names you can decide, but this component name must be the same as this one. Okay, so the second time that I call on ND2, I connect the input A, that is here, to input 3, the input B to input 4, the output C to temp 2. And now you can understand that the third time that I call ND2, I give A to temp 1, I give B to temp 2, and I give C to Z, and then you would have your end architecture. So it's quite straightforward, is that we use the port mapping technique or mapping of the ports to decide which port of my component must connect to which input, output port or signal of my design. So I wanted to use this NAND gate as a part of this bigger circuit, and I did that by first declaring it as a component, specifying its ports, and then using different instances of this component to achieve my goal. Let's look at a more practical and realistic example that we are used to seeing. We know that a full adder, which has inputs A, B and carry in, and has outputs sum and carry, we know that we can use a full adder and design it using two half adders. So how would I do that? My A gets connected to A, my B gets connected to B. The output of my sum goes to the A of the second half adder. The input C in goes to the input of my second half adder. The final sum of my half adder would be the sum of the second half adder. So the final sum of my full adder would be this, that would come from here. Now the carry is a little more interesting. I would take the carry out of the first half adder and OR it with the carry of my second half adder, and that would form my final carry. We know how to do that. Now the question is, how do I model this using the structural style in VHDL? So let's look at the example. First, obviously, I have to specify the VHDL code for the half adder. So let's look at the VHDL code for the half adder. First, I specify the entity. I specify the ports A, B, which are input of the type standard logic. The outputs are sum and carry of the type output and standard logic. It's very simple. Sum is A XOR B and carry is A and B. So a half adder, I have A, B. The XOR gives me the sum. The ANDing gives me the carry. This is my half adder. So I would write this design in a VHDL code and save it as, we've just given an example, which is lab6_2 half adder. Okay. So now, how do I use this half adder to make a full adder using the structural style? So let's take a look. First, I would specify the entity of my full adder, which has inputs A, B and C and has outputs sum and carry. Now what we will look at is, I will specify the lab6_2 half adder, call it as a component, specify its ports. If you observe that these ports are same as the ones that we had discussed in the half adder example, they must be the same. Please let me be very clear. They must be the same. Otherwise, the design will not recognize this half adder. Please understand that. They must be the same. So that said, let's continue. So I call this as a component. So this was the component declaration. Now comes the part of using this component. So let's say we have created signals as sum1, sum2, carry1 and carry2. So let's walk this design through. First, I use my first half adder, which is HA1. This is the instance name and this is the component name. So I have inputs A, B, outputs sum and carry. Okay, this is my first half adder, HA1, and then I have another guy, HA2, whose inputs are A, B, outputs are sum and carry. Alright, and then we do the port mapping. So let's go step by step. The A of my half adder is mapped to the port A of my full adder. So this goes to A. Then the B of my half adder 1, let's use a different color just for clarity. The B of my half adder 1 is connected to the B of my full adder. So this would be B. The sum of my half adder 1 is given to a signal called as sum1. Okay. And the carry is given to a signal called as carry 1. Similarly, the A of my second half adder is given to sum1 of my first half adder. Remember, it was connected to signal sum1, so effectively this is what happens. The B input is connected to the C of my full adder, so this would be C. Sum2, the sum of my second half adder is connected to the signal sum2, and the carry of my second half adder is connected to carry 2. Well, this is just the port mapping. Now we have to do some concurrent statements where we say that the carry of my final full adder is ORing of carry 1 and carry 2. So I will take carry 1, carry 2. These are these two signals, and OR them to make my final carry of my full adder, that is this one. And the final sum of my full adder, which is this, would actually be sum2, which is this one. So this would go as sum. Now if you see, this is same as this design. So we have achieved the making of a full adder using two half adders and some concurrent logic. So in my previous lecture I had mentioned that the Vhdl design is a combination of behavioral, structural, and data flow. This is basically data flow. We just understood the structural, and in some designs in the future we will see a combination of the behavioral as well. Just a quick reminder, the behavioral is the if else, the case select, those kind of statements. So I hope that this basic lecture on creating small designs and then using them in larger designs is clear. So we will see a lab on how to use this. So thank you so much. See you in the next lecture.